Chapter 2, Measurements and Calculations. Today we're going to focus on section 2.1, 2.2, and 2.3. I'm going to start with scientific notation. Before we get into scientific notation, we need to be able to recognize what a quantitative observation is. And a quantitative observation has two parts. You have to have a number and you have to have a unit. It doesn't do any good at all to have a number without telling me what it is. So in this case, this measurement right here, the number is 1 and it's a centimeter unit. As opposed to if I would have just said it's 1 and it being a millimeter unit, you can tell that there's quite a difference in the size of the unit, 10 times as much. So the number tells us a comparison and the unit tells us the scale. All right, so scientific notation is a technique used to express large and small numbers, and we use it in chemistry especially to talk about very, very small numbers. And there's rules to the scientific notation, and you have learned this in algebra, but we're going to go ahead and run through them again today. You're going to express a number as a product of a number between 1 and 10, and then use the power of 10 to indicate that number. For example, if we look at this number right here, which is 93 million, and 93 million can be expressed as a scientific notation number if we were to move the decimal point, which we know, even if we don't see it, is located right here, and we move it up to between the 9 and the 3, which gives us a number between 1 and 10, and then we would take that and we would move that decimal point 1, 2, 3, 4, 5, 6, 7 places to the left, which is like multiplying by 10 million. So 9.3 times 10 to the 7th, which is the appropriate power of 10 to change it into correct scientific notation. Any number can be represented as the product of a number between 1 and 10, and the power of 10 is going to depend on the number of decimal places and which direction it gets moved in. The number of places of the decimal point is moved determines the power of 10, and the direction determines whether the 10 is negative or positive, so whether the number is less than or greater than 1. If the decimal point is moved to the left, the power of 10 is positive, such as in 345. We move the decimal point from here up to between the 3 and the 4. It's positive because twice it's moved to the left. And if we multiplied 3.45 times 10 to the second, it would be 345. If the decimal point is moved to the right, the power is negative. If this number is smaller than 1, the decimal point was moved to the right twice to put it between the 6 and the 7, so it's to the negative second power. Let's look at the concept check. Which of the following correctly expresses 7,882 in scientific notation? So we look at this number and we have to ask ourselves, okay, where is the decimal point? And the decimal point is right here, hiding if you don't see it. And we would have to move it 1, 2, 3 places to the left, indicating a positive power. So we know automatically that this isn't going to work. And we moved it 3 places to the left, between the 7 and the 8, and the positive 3. So the correct answer is going to be C. And if you notice here on B, the decimal point did not get moved 3 times like it should have. They left it between the 8 and the 2 and still put times 10 to the third. And on A, it shows that it's times 10 to the fourth when we've actually only moved the decimal place 3 places. So the answer is C. Which of the following correctly expresses this number in scientific notation? So we look at it, and the decimal point is going to have to be moved to the right. So that's going to indicate a negative exponent, and we're going to move it 1, 2, 3, 4, 5 places to the right. So it should be 4.96 times 10 to the negative fifth. Let's look at the nature of measurement. Measurement, like we said before, is a quantitative observation that has two parts. It has the number and it has the scale or the unit. So we would say 20 grams or 6.63 times 10 to the negative 34th joule seconds. So you notice they both have numbers and they have units, so we know what it is the number is talking about. There are fundamental SI units or System International units that you need to be familiar with. For mass, we use the kilogram as the basic fundamental unit, and the abbreviation is kg. For length, we use the meter, which is M. Time, which is universal, is the second, which is the S. Temperature, the SI unit is Kelvin, and we use a capital K. Electric current is ampere, capital A, and the amount of substance is a mole, and it's abbreviated MOL. Knock off that one letter and use the abbreviation. In the SI unit, or the SI system, we use metric, and those prefixes are all the same, and they mean the same thing. So if it doesn't matter if we're talking about a liter, a meter, or a gram, when you tack on these prefixes, it means the same thing. So a megagram is going to be a million grams. A kilogram is going to be 1,000 grams, or 1,000 meters, or 1,000 liters. And you notice these end in big letters. They sound bigger: mega, kilo. When you get to deci, centi, milli, these are smaller than an entire one. So a decigram is a tenth of a gram, a centigram is 100th of a gram, and so on. And you need to memorize these and the symbols that go with them. Micro, this is a Greek symbol and Greek letter that they use for that, and it is so much smaller of a number. Notice we drop from -1 to -2 to -3. These are places past the decimal. So these are fractions of a whole. So you need to know the difference between the prefixes that mean more than a whole and the ones that mean a fraction of a whole. Length, the fundamental SI unit is meter. So we can have a kilometer, which is 1,000 meters. The meter is our base. Decimeter is a tenth of that. Centimeter is 100th of the meter. Milli is 1,000th of the meter, and so on, down to a micrometer and a nanometer. The fundamental unit of volume in the SI unit is the meter cubed, but that's really not an easy term for us to use in the chemistry lab. We use centimeters cubed. And if you look at this, this would be a meter. Remember, a meter is about the same size as a yard. So a cubic yard, and one box out of that would be a liter, or a cubic decimeter. And one unit of that, if you broke it into tens, would be a cubic centimeter. And one of the things you need to know is that a milliliter and a cubic centimeter are the same unit, only one is cubic and one is volumetric, where they both are volumetric, but the milliliters tends to refer to a liquid measure, and cubic centimeters tends to refer more to a solid measure, but they're the same unit, the same amount. If I were to take a milliliter and pour it into a cubic centimeter, it would fill it up completely. And a cubic decimeter is the same thing as a liter. Okay, for mass, the measure of amount of matter present in an object is what mass is. And our SI unit is a kilogram. It's about 2.204 pounds. And 1 pound is about 453.6 grams. And those are just general equivalencies. So choose the statement that contains improper use of a commonly used unit. Which one doesn't make sense? So we go down through here and we look at a gallon of milk is about 4 liters of milk. Well, a 2-liter soda bottle, you're familiar with that. So is a gallon of milk about 4 liters, a gallon of milk about 4 liters of milk? Is that about right? Oh, that's not too far off. A 200-pound man has a mass of about 90 kilograms. There's about 2.2 kilograms per pound, so that's reasonable. How about a basketball player having a height of 7 meters? Now, 7 meters, you can think in your mind about the size of a yard. So 7 yards. Is a basketball player 7 yards tall? Probably not. That's a little unreasonable. A nickel is 6.5 centimeters thick. Is that reasonable? Well, there's 2.54 centimeters in an inch. So every 2.5 centimeters is an inch. 6.5 centimeters is a nickel, 2 or 3 inches thick? No. So when we look at these, the last two just do not make sense. And it's really difficult. You've grown up in America where we look at English units, and so knowing what a metric unit is compared to an English unit is something you're going to have to get used to, and we'll have practice on these as we do our homework as well. And that'll be all the lecture that we have for today.